Okay, welcome back to the steam cycle lecture series. This would be the second part, looking a bit closer at the thermodynamic properties of water and steam and how we represent the steam cycle in a diagram. Well, you already know about the TS diagram. That would be the temperature entropy diagram. It is applicable to all kinds of thermodynamic processes. It doesn't matter what the working fluid is or what substances we are talking about, as long as it is a simple single substance, chemical substance, that undergoes phase changes. And in the case of just water and steam, the diagram would look approximately in this way. Well, not approximately, but exactly. You can find out there different versions of this diagram, different sizes and zooming options, but it would always look more or less in this way. The double phase dome here in red, with the wetness, constant wetness lines representing the ratio of liquid to vapor phase in the double phase dome. Blue lines, constant pressure. Green lines, not so visible here unfortunately, specific volume, constant lines for specific volume. Temperature, of course, would be a horizontal line here. Water is very easy to deal with when it comes to power cycles, and it is indeed the easiest, the cheapest, and in most cases just the best working fluid. It is also very natural to us as humans to think about water and to see it undergoing phase changes. And when we put in a perspective of actual, specific, exact temperature values and pressure values, it is also very easy to work with the diagram itself. Temperature being constant and running along the same pressure line within the double phase zone. Please don't forget that. When water or any other single simple substance is boiling or condensing, temperature and pressure are linked to each other. The easiest way to remember it, 100 degrees Celsius, 1 atmosphere, water is boiling. That's how under Celsius in Uppsala 300 years ago defined indeed the centigrade degrees and gave his name to those. Definitely we would work with evaporated water, that would be steam, somewhat above that temperature, say a couple of 100 degrees. And as soon as we exit the double phase dome and end up somewhere here where steam is superheated, that would really be our desired working fluid when it comes to steam being used as a working fluid. Remember that we see steam only if it's more or less saturated or if it is inside this wet zone. Superheated steam is not visible. It's rather like air, completely transparent. What we see in terms of fog or steaming out of a kettle, that would actually be the water droplets or the small condensing droplets inside the steam flow. The real power cycle in practice would be sliding along a constant pressure line as long as we perform the boiling process in the boiler. As soon as we let the working fluid expand, there would be a line straight down, in the ideal theoretical case, vertically down, representing the expansion. Losing temperature, losing pressure, but hopefully, in the best case, along an adiabatic line, which, thermodynamically speaking, we should rather say an isoentropic line. And why at all do we use entropy in this regard? Well, please refer back to your introductory course or to your background knowledge, which we are not going to stop here and talk about entropy more. But if you want the layman approach, or if you suddenly do not remember why at all entropy is being used, I can help you by saying that it actually has no practical sense. But in real terms, using exactly this diagram, just think about that. Entropy allows us to represent an exchange of heat, that is energy being moved from one object to another object. In the case of most often heat being transferred at constant temperature. We do not, as humans, in the way we comprehend nature, understand really how heat and energy can be transferred at constant temperature. But entropy helps us, in practice, to put this into an equation. Energy being transferred when temperature stays the same. Typical example, boiling and condensation. Representing practically steam cycles, we would rather like to work with another diagram. It is often referred to as the Mollier diagram. It also has other names, but the best with it is that, first of all, it zooms into this zone here. This area is most interesting for the practical calculation of steam expansion in the steam cycle. And here it is. The saturated steam line in red and all the areas around it. A bit below, which would be wet steam, whether boiling or condensing, and a bit above, which would be the superheated steam, within a certain range of temperatures. We do not need to extend too much this diagram because we practically do not work with steam of higher temperature than 600, at the maximum 700 degrees, in the best case, in the most modern plants. And most often we will end up somewhere here, in a typical steam plant. Whether old or new, we would be lying somewhere here. Something else that Mollier suggested, not only Mollier but many others too, is to convert the diagram from temperature entropy into an enthalpy entropy. Remember, the enthalpy is a function. It does not really exist as a practical parameter. It is something theoretically defined to help us again represent the heat content or the energy content in a fluid or in a constantly closed thermodynamic object. Enthalpy is a function of both temperature and pressure. And it is not a straight function. It is actually quite difficult to represent analytically. And this is easily seen by the fact that the constant temperature lines now in this diagram, represented in green, are actually curved. There is a complex variable actually position of the temperature lines as long as we get close to the double phase dome. The more curved it is, the more we get into or close to the double phase lines. If we are far away from the phase change area into the highly superheated fluid, you see that everything straightens up quite a lot. Temperature becomes almost horizontal, the temperature lines that is, which means that the enthalpy is more or less a direct function of the temperature and nothing else. While the pressure lines also more or less straighten up. So if we talk about air, which would be a highly superheated fluid, we are somewhere here. If we talk about steam close to its saturation zone, we always end up somewhere there. And we cannot, that is, think of steam and water as a perfect fluid or a perfect gas. They are not. They would be if we are here. Very low pressures, very, very high temperatures. Just like nitrogen and oxygen that we're breathing. But steam, in the natural way, and the processes that we would need to calculate for steam cycles, they would be in this zone. Very easy, very handy to represent the expansion with a line, ideally vertical. Now let's refer to the tutorial that we will separately talk about. And practically slightly leaning always to the right. How much it leans to the right is actually included in the loss scenario, the losses that are involved in the expansion process. Looking back at the Carnot cycle, which would be the theoretically best possible at all way to convert heat into mechanical power. The Carnot cycle in a TS diagram is very easy to represent as a square. or a rectangular, that is. Involving two isothermal processes, heating and cooling. Those would be horizontal lines here. And two isoentropic, and not only adiabatic, but isoentropic compression and expansion processes, vertical lines in this diagram. A square or a rectangular. Now, steam offering us the option of condensing within its double phase zone at a constant temperature actually helps us to approach as much as possible the Carnot cycle. The boiling process, again, being able to proceed at a constant temperature, thanks to the fact that it's a double phase or it's a phase change process, again offers us an option to represent almost as close as possible in the best case, ideal case, the Carnot cycle. The other two processes, alas, are not so easy. And this one here, compressing wet steam all the way to the saturated water line, is in practice completely impossible for an actual machine, for an actual mechanical device. So if we could arrange such a process with water and steam or any other double phase or phase change, properly said, fluid, it would almost be like a Carnot cycle. That would be the most efficient in theoretical terms. Well, disregarding the fact that there would be some other losses connected to the actual components or the mechanical arrangements, they are not important at the moment. But in practice, really, avoiding this compression and adding other clever things to convert this theoretical cycle into a practical steam expanding cycle, we would actually end up with something like this. Unfortunately, losing the Carnot potential or twisting the cycle quite far from the perfect square shape in the TS diagram, but allowing it to easily operate in practice. And not only easy, but actually it was possible to build such a cycle 300 years ago with the poor tools and machinery that humans had at that time. And the way to do that is, first of all, condense along a straight constant pressure line as much as possible, all the way down to saturated water. Ending up ideally at the saturated water line, replace the compressor with a pump. Act on the liquid, so deal only with liquid water. No gas, no vapor. Process 1 to point 2. This is the pump. That would be the main feed water pump in the steam cycle. Then heating up the liquid water along the constant pressure line in the ideal case, and sliding along also the saturated water line until it starts boiling, defined by the pressure. So this goes along the constant pressure line, which is cracked exactly in this way. All the water being converted into steam in the boiler, expanded, and the expansion process is not tricky at all. It is possible to be performed even with a slightly wet steam, and that's what the old piston engines, like the old steam locomotives, were doing. They were expanding more or less saturated steam or slightly superheated and ending up deep into the double phase zone. And then condensing, in the best case, all the steam, whether releasing it and replacing it with a new working fluid or condensing it to recycle the working fluid. This is the way to close, to complete the circuit, and thus running a practical steam cycle. This is the fundamental cycle that was really achieved in the old days, and it is exactly the same cycle that we use today. The working fluid is the same, the thermodynamic background is exactly the same, and the cycle definitely looks in this way. Well, with small twists to make it more efficient today. Those new tricks will be mentioned in the next section.